So now in today's lecture we are going to discuss the Gauss's law, right? Gauss's law or the Gauss's theorem you can. What is the Gauss's law? Listen one thing. If these are the number of point charges, right? For example, this is the Q1, Q2 and Q3, suppose. There are 3 point charges are there, right? Like this. So if you draw a closed surface, if you consider a closed surface, this surface is called closed Gaussian surface. Gaussian surface, right? Closed Gaussian surface. Is it clear? Closed Gaussian surface. So the net outward flux, this is the flux linked with this closed Gaussian surface like this, right? According to Gauss's law, according to Gauss's law, right, the net outward flux linked with closed surface, right, linked with closed Gaussian surface is equal to 1 upon epsilon naught times the charge enclosed in it. Right? This is the Gauss's law, right? That is the net outward flux. Listen one thing. If the small flux you write the E dot ds, right? What is the net outward flux? This is the integration of the net outward integration of E dot ds is nothing the net outward flux. So net outward flux is equal to 1 upon epsilon naught into charge enclosed in it, right? This is the charge enclosed. Is it clear or not? So net outward flux is nothing but E dot ds is equal to 1 upon epsilon naught into Q enclosed. This is called the Gauss's law. Is it clear or not? E dot ds is equal to 1 upon 10 epsilon naught Q enclosed, right? This is the Gauss's law. How do we use this to get the electric field? We will see in the next, right? Copy this first. So how to solve this question, how to use this? For example, I'm giving you one illustration. For example, this is the 2 microcoulomb charge, this is the 1 microcoulomb charge, this is minus 1 microcoulomb charge, this is the 2.5 microcoulomb charge, this is 1.5 microcoulomb charge, right? So this is, I am writing minus 0.5 microcoulomb charge like this, right? So these are the charges present in the space, right? Like this. So if you consider if this is the one Gaussian surface, right, and this is the another Gaussian surface like this, fine. So this is the Gaussian surface S1, this is the Gaussian surface S2. You have to find the flux, linked with, right, surface S1 and S2, right? Copy this. So how to write the answer? Listen, although there is no calculation formula to find the answer, find the flux link with this surface, right? But with the help of the Gauss's law or Gauss's theorem, you can say we can write directly the flux enclosed. According to this, the outward flux linked with this surface is nothing but 1 upon epsilon naught, or you may write charge enclosed divided by epsilon naught. Epsilon naught is as it is. What is the charge enclosed in it? In this surface, the charge enclosed is 2, 1 and minus 0.5. This 1.5 and 2.5 charge is not enclosed by the surface S1. So surface by S1 is nothing but 2 plus 1 minus 0.5 is equal to 2.5 microcoulomb divided by epsilon naught, right? You may write 2.5 into 10 to the power minus 6 divided by 8.85 into 10 to the power minus 12. So 2.25 is into 8.85 into 10 to the power 6, right? So when you will find this calculation, you can get the answer, right? The charge enclosed. Is it clear? This is the net outward flux in Newton per coulomb meter square. The net outward flux means sometime you may write it is as a E dot ds integration for the closed contour S1, right? This circle tells that we are finding the surface linked with a closed surface S1, right? So this is the value of the outward flux for the surface S1. In the same way, for this surface S2, right, the outward flux is equal to what? Charge enclosed divided by epsilon naught, and this is called the Gauss's law. This is called Gauss's law, right? Gauss's law. So the charge enclosed is what? Through this closed surface is 1.5 plus 2.5 minus 0.5 divided by epsilon naught. Charge enclosed divided by epsilon naught. So this is how much? 4. This is 3.5 into 10 to the power minus 6. 3.5 microcoulomb divided by 8.85 into 10 to the power minus 12, right? When you will simplify, you will get the answer in Newton coulomb into meter square, right? Copy this. For example, we have shown that if this is a closed surface, right, and this is the closed surface, and suppose the charge is placed over here and nothing charge is present in this case. So if this is the sphere, what the electric flux, tell me, if this is the sphere of the radius r and the charge is placed outside, so what is the flux? Find flux linked with closed surface, linked with this closed sphere, right? So listen one thing, how to find? By the Gauss's law we can explain this, although we have done this, right? According to Gauss's law, apply the Gauss's law. What is that? The net outward flux is equal to charge enclosed divided by epsilon naught. If you consider nothing is enclosed in it, what is the charge enclosed here? 0. So what is the outward flux? Say outward flux is nothing but, the outward flux is nothing but may be written as E dot ds is equal to 0. You understand or not? What does it mean? If, right, we have seen this earlier also, not only for the solid sphere, if any shape of the closed, this is the closed surface, any shape of the closed surfaces, if this is the charge q, right, because of charge q, what the flux is entering, the same flux will come out. Is it clear or not? This is the one thing we have explained it earlier, but with the help of the Gauss's law it can be verified also, right? Because no charge enclosed by this Gaussian surface, all the charge is present outside. So what is the net outward flux linked with this surface? Say 0. In the same way, what the flux is entering, the same flux is going out from the surface. Is it clear or not, you tell? Right, like this. Fine. The inward flux and the outward flux, both flux are same, right? Copy this. So very important question I am telling you. Suppose this is the Q1 over here, this is the Q1, this is Q2, this is Q3, right? This is Q4, this is Q5. Is it clear or not? So if you consider this is the Gaussian surface, right? So what is the flux linked with this Gaussian surface? If this is the closed surface, right, you may assume this is to be S. So how to write the Gauss's law? The net outward flux is charge enclosed divided by epsilon naught. So what the charge is enclosed by this closed surface? Only the Q1, right, plus Q2 plus Q3, right, Q1, Q2 upon epsilon naught. Q4 and Q5 are outside the closed surface, therefore we are not considering this. And this is the net outward flux, which may be written as the integration of E dot ds. You understand this? So this is the net outward flux for this Gaussian surface as shown in figure, right? For example, now This is the expression for the Gauss's law, right? What is the E? E is the electric field. Suppose at this point the electric field is what? Say E, right? So if this is the electric field E, right? Suppose the elemental charge, elemental surface area ds you have taken like this, and this is the elemental, this is the electric field over there. Although the electric field at this, at different point here, the electric field will be different value, right? It is very much clear, right? I am asking you, this electric field is due to which charge? Only q1, q2, q3, or all the charges q1, q2, q3, q4, q5? You tell. This electric field is due to, at this point, any point, the electric field in this integration written is due to q1, q2, q3 or q1, q2, q3, q4. You have to tell, right? I am telling you now, the electric field is, although to find the electric field the charge enclosed q1, q2, q3 are taken in the calculation, but at this point the electric field is due to, right, due to all the charges, all the charges present, right? All the charges present in space. Is it clear or not? Whether they are taken into account in the Q enclosed or not. So this electric field is due to all the charges Q1, Q2, not only the Q1, Q2, Q3, right? Whether they are enclosed or not, but this electric field is the total electric field due to all the charge present over there, right? You have to understand this. Also, listen one thing, the one important point, the electric flux, right, does not depend upon the shape of Gaussian surface. Is it clear or not? For example, if this is the q1, q2 and this is the q3, whether you choose the Gaussian surface or whether you choose this Gaussian surface, the shape of the Gaussian surface S1 and S2 are different, but the charge enclosed is q1, q2, q3, and therefore the net flux linked with S1 and S2 is same. It does not depend upon the shape of the Gaussian surface, rather it depends upon the charge enclosed, right? Charge enclosed. Is it clear or not? Right? Copy this. Now we can write the application of Gauss's law. Applications of Gauss's law, right? Gauss's law. The application of Gauss's law. First, the electric field due to point charge, right? Although we know the electric field due to the point charge is kq upon r square, but with the help of this Gauss's law, we can find the electric field due to symmetric charge distribution. Application of the Gauss's law, we are going to find in different cases the electric field due to the symmetric charge distribution, right? To find electric field due to symmetric charge distribution, right? Only for the symmetric charge distribution we are able to find the electric field with the help of the Gauss's law. Not due to all the charge distribution we cannot find, right? For example, first the point charge is supposed to be the q, and here at the point p at distance r you want to find the electric field. To find the electric field, the first step is that you have to choose a symmetric Gaussian surface. For this point charge, the symmetric Gaussian surface is a closed sphere like this. This is the symmetric charge distribution. This is the symmetric Gaussian surface. Why it is? Because the electric field is what? electric field is radially outward from this charge, right, like this. If you consider this is the Gaussian surface, this is the closed Gaussian surface. If you consider, is it clear or not? Right. So at this point, any point you can write, suppose the electric field is E. So apply the Gauss's law. Apply Gauss's law. Right. What is the Gauss's law? The net outward flux is charge enclosed divided by epsilon. So if this Gaussian surface is this, so what is the charge enclosed by this Gaussian surface? Only Q upon epsilon naught. And the outward flux is what? Say E dot ds. Is it clear or not, you tell? Is equal to Q upon epsilon naught. Listen one thing. Here, if you consider this is the electric field, right? This is the electric field at this point, and the ds vector are in the same direction. So what is the theta over here? Say 0, right? If theta is equal to 0, you may write E ds cos 0 is equal to Q upon epsilon naught. Cos 0 is 1. Listen one thing. If you write the electric field at every point, the magnitude, although the direction of the electric field at different point is different, but if we consider the magnitude, the electric field on the surface of this sphere is what? Is E. So E is constant, it comes out from the integration, and this is the ds upon Q epsilon naught. What is the ds? ds is the elemental area of the elemental part, right? And if you integrate this, what will you get? Integration of ds mean the total area of the spherical shell you have to write. So the integration, this circle represent the closed surface integration we are doing, is equal to what? Say 4 pi r square. What is the area of this sphere, spherical shell? It is 4 pi r square. So E into 4 pi r square is equal to Q upon epsilon naught. So electric field is Q upon 4 pi epsilon naught into r square. Is it clear or not? So we have found the electric field due to the point charge with the help of the Gauss's law. We have seen this with the with the help of the Coulomb's law. We have shown the definition of the electric field is force per unit charge, right? So but without Coulomb's law, with the help of the Gauss's law, we have found the electric field, right? Important thing is that this electric field we are able to find if the electric field or the charge distribution is symmetric. The electric field is symmetric about the charge distribution, then only we can find the electric field with the help of the Gauss's law. Not due to all the charge distribution we cannot write or we cannot find the electric field. For example, if this is the Q1, Q2 and Q3 and you want to find the electric field with here, so the important point I am telling you, important point, right? What is that? If you want to find the electric field due to this charge distribution, the electric field at the different point will be the different. It is unsymmetric. Although when you will apply the Gauss's law, right, for this Gaussian surface, the net outward flux is equal to charge enclosed divided by epsilon naught, right? Net outward flux is equal to charge enclosed divided by epsilon naught, and the charge enclosed is Q1 plus Q2 plus Q3 divided by epsilon naught E dot ds. Listen one thing. The Gauss's law is valid. Gauss's law is valid. No problem. This is for unsymmetric charge distribution, right? Unsymmetric charge distribution. If you consider the Gauss's law, these are the point charges. Gauss's law is valid, but electric field cannot be found, right? Cannot be found. Why it cannot be found? Because this electric field at the different point will be the different. At different point will be the different. In this case, the magnitude of the electric field was same on each and every point on the surface of the sphere. That is why this electric field come out from the integration, right? But in this case, when you will try to find the integration, the electric field is not constant. So since electric field is not constant. And we are unable to calculate this integration and constant, and we are unable to find this integration, right? If we are able to do this integration, then we can find the electric field. But how to do integrate? Because when you will take EDS cos 0, the electric field cannot be taken outside from the integration. Why? Because at every point the electric field will be different, right? So therefore, the very important point I am telling you, you have to understand, the Gauss's law is always valid whether the charge distribution is symmetric, whether the charge distribution is symmetric or the electric field is symmetric, whether the charge distribution is unsymmetric. But electric field can be found in this case, but for unsymmetric charge distribution, electric field cannot be found because we are unable to integrate this integration, right? Because E is not constant. You understand or not? Right, copy this. So the second application is the electric field you have to find due to infinite line charge, line charge having linear charge density lambda, having linear charge density, right, lambda coulomb per meter, linear charge density. Suppose this is the line charge, infinite line charge, right, like this. And the linear charge density is lambda coulomb per meter, and you want to find the electric field at distance r at this point, right? This is the question, right? Copy this first. Listen one thing. Although we know for the infinite line charge, what was the electric field, if you remember? Say 2k lambda upon r, right? With the help of the integration and the Newton's law, Coulomb's law, we have found this. But now this time the same expression we are going to find with the help of the Gauss's law. To find the electric field with the Gauss's law, the first condition is that the charge distribution should be the symmetric, and you have to choose the Gaussian surface which is also symmetrical. So in this case, the vertical cylinder, the Gaussian surface will be the symmetric Gaussian surface, right, for which if you consider the electric field, right, is away from this linear charge radially outward like this, right? This is the electric field. Are you getting? Like this. Fine. So at this point the electric field is what? Say E. This is the E. So at the every point on this cylindrical Gaussian surface, right, the electric field is what? Say constant everywhere here. So that is why the vertical cylinder I am taking. We cannot take the spherical surface in this case, because the electric field will be the different at different point. So first I will tell you that for which type of the charge distribution you have, which type of the Gaussian surface you have to choose. Then you will understand automatically after taking few examples, right? So here the vertical cylinder is the Gaussian surface. This is the vertical cylinder is the Gaussian surface, right? The length of this vertical cylinder I am taking the L. Is it clear? Everywhere the electric field is E. I am making the figure once again like this. This is the symmetric charge distribution and this is the Gaussian surface, right? First of all, if the length is L and the lambda coulomb per meter is the linear charge density, we write the Gauss's law, right? What is the Gauss's law? The net outward flux is equal to charge enclosed divided by epsilon naught. So can you tell me what is the charge enclosed in this Gaussian surface, in this closed cylinder? What is the charge enclosed? This is the charge enclosed. This is the charge enclosed, right? All this charge is the enclosed by this Gaussian surface. This charge and this charge is not enclosed. You understand? So how to find? If this is the lambda coulomb per meter, mean in 1 meter the charge is lambda coulomb. So in L meter, what is the charge? Say lambda into L. Is it clear? So the charge enclosed is nothing but lambda L we have found. right? Now the outward flux we have to calculate E dot ds is equal to charge enclosed what, lambda L upon epsilon naught. Now we have to integrate, or we have to find the outward flux, right? So how to find the outward flux, you tell. This is the closed Gaussian surface. There will be the three surfaces, the S1, this is the one surface, this is the S2, the another surface. Here the electric field is like this, right? And the surface area vector is in this direction. So what is the angle between them? This is the surface, right? And this is the electric field. So what is the angle between them? Say 90 degree. So for this surface, the flux link is what? You will say 0. You understand or not? Right. And for this surface also, the electric field is always perpendicular to the surface S2 vector 90 degree. So the flux link with this is also equal to what? 0. Right. So you may write in this way. The outward flux is linked with S1, S2 and the lateral surface. If this is the cylinder, this is the one surface, this is the another surface, and this is the lateral surface. So the phi 1 plus phi 2 plus phi 3 is equal to lambda enclosed divided by epsilon naught. This is 0, this is 0, right? This only we have to find. So what is the flux you will find? You will write for this lateral surface, right? The electric field is coming out everywhere is what? Say E. Is it clear? So E, and what is the area? Say 2 pi r. 2 pi r. What is the area of, this lateral surface? 2 pi r into L. So the flux coming out from this lateral surface is nothing but E into area. 2 pi r, r is the radius and L is the length, 2 pi r. So this is the value of the phi 3, right? So the phi 3 is equal to lambda L upon epsilon naught, right? You may write in this way also. The E dot ds is equal to lambda L upon epsilon naught, right? If you are taking the elemental ds vector, the electric field will be E, the theta is 0, right? So here you can write E ds cos 0 is equal to lambda into L. Electric field come out from the integration into ds, lambda into L. If this is the elemental area, so what is the total area of this surface? The integration of ds is nothing but 2 pi r into L. So here E into 2 pi r into L, you can write the total flux, right? This is the total flux we have written. E multiplied by area. This length is cancelled out. So the electric field may be written as 2 pi epsilon naught lambda upon r. And this is what? K value is 1 upon 4 pi epsilon naught. So therefore it may be written as 2k lambda upon r. So this is the electric field as a function of r for this line charge distribution at any distance r, right? So this electric field we have found for this symmetric charge distribution. Now the next application is the electric field you have to find due to uniformly charged spherical shell, right? Uniformly charged spherical shell. If this is the sphere, right, and this is the shell, all right, the total charge is Q, and you have to find the electric field due to this charge distribution, right? In this case there will be the two cases, right? Inside electric field from r is equal to 0 to r is equal to capital R. Suppose the radius is to be r and this is r. This is the electric field. Just below this we will make the graph and we will try to find the electric field due to this charge distribution, right? First copy this, then I will explain. So let's see how to find the electric field due to this charge distribution. Listen one thing, the electric field is always away, right? In the gravitation we have also done that, right? Here I will write the two cases. The case 1 inside. Inside mean we are going to find the electric field at a point P which is a distance r, right here. Inside mean the point may be at this point, at this point, at this point, like that. The r distance may be from 0 to capital R, right? Or just small r you can write. Is it clear or not? So for inside, the electric field, to find the electric field, the charge distribution is symmetrical, the electric field is radially outward. What type of the Gaussian surface you will take? You will take the spherical Gaussian surface, right? Here the Gaussian surface is E, you will apply the Gauss's law. The net outward flux is equal to charge enclosed divided by epsilon naught. So if this is the Gaussian surface, all the charges outside, what is the charge enclosed by this Gaussian surface? For this Gaussian surface, the charge enclosed is 0, and therefore if you write the E dot ds, right, if you assume the elemental portion of the ds vector, the electric field, suppose the E, right? So if you write like this, so it is equal to 0, E integration of ds is equal to 0. Integration of ds is nothing but 4 pi r square. Which r? Small r or capital R? For this spherical shell, this is the shell, small shell, the area is 4 pi r square, but electric field is what? 0. Is it clear or not? It means inside the spherical shell, no electric field is present. Is it clear or not? Right? Copy this first. I'm making this once again. The electric field is E, the integration, the elemental area is ds, right? Copy this now. So in the case 2, yes, the case 2, the outside, you have to find the electric field, and the value of the outside is outside from capital R to infinity, right? Suppose this is the figure I'm making this side, you can make here, right? And this is the charge, capital Q, present on the spherical shell of radius r. This is the charge Q, and this is the point P, which is at separation r, and you have to find the electric field at this point. So what will you do? You will assume this is the Gaussian surface, the spherical Gaussian surface, right? Here the electric field at this point, because this is symmetric, the magnitude is E, although the vector will be the different. So you will assume this is the ds vector, this is the E vector, right? So you will apply the Gauss's law. Apply the Gauss's law. What is the Gauss's law? The Gauss's law. The net outward flux is equal to charge enclosed divided by epsilon naught. Is it clear or not, you tell? So what is the charge enclosed by this Gaussian surface? All the charge is enclosed by this Gaussian surface. So this is equal to Q upon epsilon naught. This is the E dot ds, right, is equal to Q upon epsilon naught, right? Listen one thing. If you consider this is the E dot ds is equal to Q upon epsilon naught, the electric field is constant, so it comes out from the integration of ds, Q upon epsilon naught. If this is the elemental area ds, so if you integrate this, what is the total area? The integration of ds is nothing but 4 pi r square. You tell me which r square you tell. Say 4 pi r, small r square, because this is the capital R, we have to find the area of this Gaussian surface. So you will write it is 4 pi r square Q upon epsilon naught, which may be written as 1 upon 4 pi epsilon naught and Q upon r square. Is it clear or not? So the electric field is nothing but KQ upon r square, right? The electric field, I am writing this side, this electric field is nothing but as a function of r, and the electric field is inversely proportional to r square. Here the small r values varies from capital R to infinity. So at surface, at r is equal to capital R, what will be the electric field, you tell? At r is equal to capital R, KQ upon r square is the electric field. At r is equal r tending to infinity, when it tending to infinity at very far away, the electric field at infinity, when you will put 1 kq upon infinity, so 1 upon infinity become 0, and here the electric field varies inversely proportional to the square of the distance between them. Therefore, if you draw for the inside, this is the inside electric field, no electric field is present, but if you consider the outside, the electric field outside is like this, right? So it starts from the surface of the spherical shell and elongated up to, and it is present up to infinity. So on the surface at this point, at r is equal to r, what is the value of the electric field? You will say it is, this electric field is nothing but kq upon r square, and at infinity the electric field is 0, right? So it varies like this, right? So this electric field is inversely proportional to r square. So at any point p, the electric field outside here, electric field is kq upon r square, and inside, at any point inside, the electric field is 0. So this is the inside electric field, it is 0. At surface, kq upon r square, and the outside electric field is this. You understand, right? Copy this. So now the next topic is what? The electric field due to the solid sphere. Electric field due to solid sphere uniformly charged, right? Having the volume charge density, right? The volume charge having volume charge density rho, right? Like this. Rho mean rho coulomb per meter cube is the volume charge density. If this is the sphere, all right, right, this is the sphere of the radius r, this is the capital R, and the charge is distributed over the volume, right? Like this, over the volume the charge is distributed, and this is the center. Now you have to find the electric field, right? Also you have to draw the graph of the electric field, right, as a function of r. R is the distance from the center, right? From r is equal to 0 to r is equal to capital R, this is the point inside. We will discuss the two cases, the electric field inside the solid sphere, and from r is equal to r to infinity, the outside. Suppose the total charge assumed to be the q. The total charge distributed is what? Q. Either the answer of the electric field we will write in terms of q, or we can write in terms of rho also, right? So I am assuming the total charge is q. So what is the volume charge density? Rho is the volume charge density, total charge divided by total volume. So this is the volume charge density, coulomb per meter cube, you may write, right? First copy this, then we will make the two cases inside and outside, right? Copy this. So I will write the two cases over here, the one by one. Inside, the inside means the point here is at some distance r, like this. So at this point you have to find the electric field. To find the electric field at this point, you have to choose a Gaussian surface. This is the symmetric charge distribution, and therefore the electric field will be the symmetric. So therefore the symmetric Gaussian surface you have to choose. You have not to choose the cylinder, right? Cylinder is not symmetric Gaussian surface for this charge distribution. Rather the spherical, this is the sphere of the radius r is the symmetric Gaussian surface. So that at every point the electric field, although the direction is different, but the magnitude at every point will be the same. You understand or not? So choose this Gaussian surface inside. The inside mean the small r distance is greater than 0 and less than r. You can write in this way, and apply the Gauss's law. Apply Gauss's law. What is the Gauss's law? The net outward flux linked with this Gaussian surface is equal to charge enclosed divided by epsilon. So can you find first the charge enclosed? Charge enclosed in this Gaussian surface, right? This is the Gaussian surface. We have assumed this is the ds vector and this is the electric field vector. So in this case, the charge enclosed you have to find first. How to find the charge enclosed? Using the unitary method, right? How? If you consider the total volume, the volume is nothing but total 4 upon 3 and the total charge distributed over the volume is capital Q. For 1 meter cube, the charge is Q upon 4 upon 3 pi r cube. You understand? This is 4 upon 3 pi r cube. So what is this volume? This volume is 4 upon 3 pi small r cube. The total charge is pi r cube, 4 upon 3 pi small r cube. So it is cancelled out. So the enclosed charge is nothing but q upon r cube into r cube. Is it clear or not, Ethan? Right. So this is the enclosed charge for this expression. And what is the outward flux? The outward flux, because it is a closed Gaussian surface. So what is the flux formula? Integration of E dot ds, and the charge enclosed is q upon r cube into small r cube, and this is the epsilon naught. Is it clear or not? Right. So listen one more thing. If this E is constant, listen, E and ds vector in most of the cases, right, at 0 degree. So E ds cos 0, it will be what? E ds cos 0, right, and it is the integration. So electric field is constant, so it will come out from the integration, and only integration of ds is equal to q r cube upon epsilon naught, capital R cube will be there. What is the ds? ds is the elemental area of this small sphere. If you integrate this, what is the integration of ds? Please tell. It is nothing but the total area of the surface, 4 pi r square. Which r? Capital R, small r. If you consider this the spherical shell, so small r square is the area. So integration of ds, I am writing it is 4 pi small r square q r cube upon epsilon naught capital R cube. If you simplify, this is the r square, this is the r cube, right? So E may be written as q upon 4 pi epsilon naught small r upon r cube. Is it clear or not? So this is the electric field as a function of r. It may be written as k q r upon r cube. So this is the electric field inside the sphere, right, at distance r. I am writing this like this, right? So this is the electric field as a function of small r, right? What is the value of the small r? The small r domain is r is equal to 0 to r is equal to capital R, right? Although in mathematics you may be put the equal or less than, no problem at all, right? At center mean at this point, what is the electric field? When you will put r is equal to 0, so this electric field is 0. It means at center the electric field is 0. It is equal to capital R on the surface, what is the electric field? When you will put capital R, kqr upon r cube is equal to kq upon r square. You understand this thing or not? So kq upon r square is the electric field. You may write in this way. This is the kq upon r square at r is equal to capital R. Is it clear or not? One more thing. Here the electric field is directly proportional to r. Is it clear or not? Right. Electric field is directly proportional to r. It means inside the sphere. How does the electric field vary? The electric field vary linearly. This is the case of the inside, right? So inside the electrostatic field, right, inside the uniformly charged sphere varies linearly like this, right? And you have to remember this formula for the inside part, right? Copy this. So now I will try to find the electric field outside. So the outside, case 2, the outside the electric field. Outside means the point is outside. mean this distance r is greater than capital R and less than infinite. Is it clear or not? Outside. Fine. So I'm making the figure at this point. Here, this is the uniformly charged sphere. This is the center of the sphere is the O. All right. And this is the point P. Right. So this is the distance R. This is the total charge capital Q. And listen one thing. This is the charge capital Q. So this all this charge can be assumed to be present on its center for the outside point which is present at distance r, right? Listen one thing, not like this. You can think if this is the point P at distance r, we have to solve the electric field with the help of the Gauss's law, although with the help of the Coulomb's law we can also write. So for that you will assume a Gaussian surface. This is the spherical Gaussian surface. All right. So, and you will assume the ds vector like this. This is the electric field vector. The charge distribution is symmetric at this every point. The electric field will be the E. The magnitude is E. So, if this is the Gaussian surface, apply the Gauss's law. What is the Gauss's law? Gauss's law. Gauss's law is the net outward flux is equal to charge enclosed divided by epsilon naught. Can you tell me if this is the spherical Gaussian surface, what is the charge enclosed in it? All the charge enclosed is capital Q upon epsilon naught. The outward flux is nothing but E dot ds. Fine, is equal to Q upon epsilon naught, and the electric field comes out to be constant. It is comes out from the integration Q upon epsilon naught, and the ds vector is what? Say 4 pi r, small r square. Why? This is the ds, and the integration of ds is nothing but the spherical surface area of this of small r, right? So this is Q upon epsilon naught. So you may write this, the electric field is equal to 1 upon 4 pi epsilon naught and Q upon r square. You may write it is KQ upon r square is the electric field. Is it clear or not? So this is the electric field as a function of small r, right? Here the r value varies from capital R to infinity, right? That is from the surface to the infinity, the point. So on the surface, on just surface at r is equal to capital R, right? If you put capital R is equal to what? KQ upon r square is the electric field at this point, right? And at r tending to infinity at very long distance, when you will put infinity, 1 upon infinity is equal to 0, and the electric field here is inversely proportional to r square. So if you make the graph for the electric field versus distance r for out point, for outside of this sphere, the electric field is like this. Is it clear or not, Newton? And this electric field is inversely proportional to 1 upon r square, right? And this is for outside, right? This is the thing, right? So you can copy now. So listen one thing. In terms of rho also, it is very important to write the formula. For the outside there is no difference, but for inside, right, the important this is the very important expression for the electric field inside. What the inside electric field formula we have found? It is KQR upon small r cube. It is the electric field as a function of r inside. But in terms of, this is the electric field in terms of capital Q, the charge distributed over the sphere. Now, can we write it in terms of rho? Yes. The Q value is nothing but rho into 4 upon 3 pi r cube. So, the electric field inside I am writing, right, the K value is 1 upon 4 pi epsilon naught. This is the r cube, right, and this is Q into r. What is Q? Rho into 4 upon 3 pi r cube. This is the capital Q and this is the small r, right? It is small r. So the 4 pi will cancel out, right? So rho, right, this is for 1 minute, Q is equal to rho into Q is equal to rho into 4 pi r cube. This is the rho. This is r square, capital R square, capital R cube, sorry. Rho into 4 pi capital R cube it is. Right, please make it correct. So this 4 pi also cancel out, the r cube is also cancel out. So here rho upon 3, and this is the epsilon naught, and this is the small r. So this is the electric field is equal to rho r upon 3 epsilon naught. You have to remember, right? You have to remember this because it is very useful. Remember, right? In terms of vector, suppose this is the uniformly charged sphere, right? And the volume charge density for this sphere is rho. This is the center. At this point, at the separation r, what is the electric field over here? The electric field is nothing but rho r upon 3 epsilon naught. Rho r upon 3 epsilon naught is the electric field. Is it clear? Rho r upon 3 epsilon naught in vector form. In vector form. Listen one thing. If this is the origin, you assume to be the origin, this is the point P whose distance is r. So if you assume this is the position vector, so the electric field vector and the position vector are in the same direction for the positive charge distribution. So therefore, the electric field may be written as rho vector r upon 3 epsilon naught. So this is the vector form which is important to solve some typical question, right? So inside the uniformly charged sphere, this electric field you have to remember. Although in terms of Q, you have to also remember this, right? Copy now. So the next application you may write the electric field you have to find due to uniformly charged sheet having surface charge density sigma, right? Sigma coulomb per meter square. I think we have not done this. Please tell. With the help of the Gauss's law, if this is the uniformly charged sheet, right, like this, have we done Varsha or not? I did not remember. For this case, if this is the sigma coulomb per meter square, you have to find the electric field with the help of the Gauss's law, right? It is extended to infinity. At distance r, at this point, you have to find the electric field. You understand or not? Right? Copy this. So how to find the electric field? With the help of the Gauss's law, we are going to find, although with the help of the integration, the electric field sigma upon 2 epsilon naught, we have done this earlier, right? If you remember, we found first the electric field due to this sheet. This is electric field due to this disk. The electric field was sigma upon 2 epsilon naught 1 minus cos theta. And for the, if disk is extended up to infinity, the theta become 90 degree and cos 90 becomes 0, and the answer comes to be sigma upon 2 epsilon. We have done this earlier with the help of the taking the small ring and then integrate this. But with the help of the Gauss's law, it can be done in an easier way, right? It can be done in easier way. How? You have to choose the Gaussian surface such that this Gaussian surface must be symmetrical. In this case, I am telling you first, then you have to understand. The Gaussian surface is taken to be the horizontal cylinder like this, right? This is the horizontal cylinder. You have to take the Gaussian surface because the electric field due to the plane sheet is constant. If you remember, we have done this, the plane sheet, the electric field is what? Constant everywhere. So if you are choosing this is the Gaussian surface, the horizontal cylinder, and the area of this cylinder is what? Say assume to be the S. Fine. So, and if you consider this is the area and this is the charge enclosed, right? So this horizontal cylinder is the Gaussian surface. right? Gaussian surface. Gaussian surface is the horizontal cylinder, right? And this is the charge enclosed. Although the charge is present on the sheet everywhere, but if you consider this is the horizontal cylinder, so on this cross section area, this is the charge enclosed by this horizontal cylinder, right? If the surface area is A, this is the point P where we have to find the electric field. So for this Gaussian surface, this is the horizontal cylinder. How many surfaces are there? This is the one cross section, this is the another cross section, and this is the lateral surface. But due to this charge distribution, the electric field is constant everywhere. And this electric field is what? This electric field is away from the sheet like this. Here, this side the electric field. We don't know the value of the electric field, therefore I can write this is the E. In the same way, in this side also, the electric field, right, will be same, right? The electric field is assumed to be the E. Is it clear or not? So now you can apply the Gauss's law. You can apply the Gauss's law. What is the Gauss's law? The net outward flux is equal to charge enclosed divided by epsilon. Right. If this is the horizontal cylinder, this is the horizontal cylinder, this is the charge enclosed. Can you write the charge enclosed here? Yes. If the surface charge density is sigma coulomb per meter square, it means in 1 meter square how much charge is? Say sigma coulomb. You understand? So what is the area? The area is to be the S. So in S area, this charge enclosed is sigma into S. So the charge enclosed is nothing but sigma into S. Sigma into S. Sigma into S. Fine. It is that. Now you have to find the outward flux, right? First copy this, then we will write this expression. So you have to find the outward flux. If you consider this is the horizontal cylinder like this, right? And in the sheet is in between like this. So the electric field is from the sheet. If this is the sheet, the electric field is like this, right? It is coming out, going in this way, coming out from this surface like this, right? Like this. Is it clear? And in the same way, this is the electric field, this is the electric field, this is the electric field, like this. Is it clear or not like this? So if you there are the three faces for this cylinder, the three faces are there, or the three surface. This is the 1, 2. For this case, the phi 1, can you write? Yes, the electric field multiplied by area, because EDS cos 0. Here the electric field and the area vector are in the same direction. Here also the area vector and the electric field in the same direction. If you consider the phi 2 link with the surface, the E into S will be again the electric flux. The electric flux link with this E into S again, right? And what about this? The electric field is in this direction. And if you consider the elemental surface area like this, so this is the DS vector or the S vector, whatever you write. Here the angle between the electric field and the S vector is what? 0, because the electric field is in this lateral surface, along this lateral surface. So if you consider this is the lateral surface, this is the lateral surface, the flux link with this lateral surface is 0. Are you getting? So the total flux I am writing, the phi 1 plus phi 2, right, plus phi 3 is equal to sigma S upon epsilon naught, right. So the phi 1 is ES, phi 2 is ES, right, and phi 3 is 0, sigma into S upon epsilon naught. 2 into S is equal to sigma into S upon epsilon naught. The SS will cancel out. So electric field is what? Sigma upon 2 epsilon naught. Is it clear or not? The same electric field was found by doing the integration of the disk, and that's all, right. So sigma upon 2 epsilon naught is the electrostatic field. And you have to also, the very important thing is that this is the one phase, or you can say this is for the non-conducting sheet. Non-conducting sheet. The electric field is sigma upon 2 epsilon naught due to the non-conducting sheet. or due to the one phase, right? Copy this. I'm asking one question. This is the infinite charge distribution. This is the symmetric charge distribution, and we are able to find the electric field. But if the disk is there, only the disk is there, right? Can you find the electric field at over there? No, because the electric field is what? Unsymmetric due to this. The unsymmetric electric field is there. So we cannot find the electric field with the help of the Gauss's law. But if it is extended to up to infinity, the electric field become what? Electric field become constant and uniform, right? Constant and symmetric. So that is why we are able to find the integration or the flux. Basically we have to find. In this case we cannot write the flux, fine, because if you try to make the Gaussian surface like this, right, the electric field is like this, how would you find the flux? So we are unable to find the flux because the electric field is like this. In this case the electric field is away from the surface, uniform electric field everywhere. In this side also the uniform electric field. That is why we are able to find the, or we are able to write the electric flux link with this surface, right? Copy this fast. So listen one thing, we have found the electric field due to the non-conducting sheet. Non-conducting sheet, I am giving you an example of the non-conducting sheet. Suppose this is the sheet, right? This is the paper and it is non-conducting. The property of the non-conducting sheet or the insulator is that if you put the charge on this surface, right, the charge will remain on where it is placed, it will not move, right? So if you consider this is the non-conducting sheet, the non-conducting sheet I'm making like this. So if you put the charge over here, right, on the one side, and the surface charge density is sigma coulomb per meter square. Therefore, because of this, at any distance, the electric field does not depends upon the distance, and it is given as sigma upon 2 epsilon naught. In the same way, this side is also because of this surface, right? This is the electric field due to non-conducting sheet, not conducting infinite sheet, right? Like this, sigma upon 2 epsilon naught. But if you consider the conducting sheet, electric field due to infinite conducting sheet. Conducting sheet, what type of the conducting sheet? Mean like iron, aluminium, copper, any conductor. The property of the conductor, I will explain this later also, but here you have to understand, if the property of the conductor is that if you give the charge, suppose this is the copper plate, if you give the charge will not remain on this side, rather the charge will come on the surface on this side also. The charge, the property of the conducting sheet, charge remains on the surface, right, remains on both side of surface, you understand or not? Both side of surface, no charge is present inside the conducting sheet. So if this is the conducting sheet, suppose this is a conducting sheet, very thin sheet it is. So if you give the charge, the charge will be on both side, charge will be on this side, also on this side, right? Although if this is the thin, you can make a thick sheet in place of this, like this. This is the sheet, right? Like this. This is the conducting sheet. So if charge is present on the left side of the sheet, this side, automatically, this is the property of the conductor. If you put the charge over here, only this point, so the charge will come on the every point on the surface, like this. Is it clear or not? So therefore, for this sheet, what is the difference between the non-conducting and the conducting? The surface charge density, if it is sigma, so not only the one side, rather on the other side also the electric field, or on the other side also the surface charge density will be present. So if you want to find the electric field at distance r here, So you have to choose again the Gaussian surface. Suppose this is the horizontal Gaussian surface you have chosen. So this time the charge enclosed by this Gaussian surface is, this is the charge, this is the charge. Is it clear or not? This time the charge is enclosed by this surface, horizontal surface is this side, also this side. In this case, if you have chosen the Gaussian surface, the charge is present on the one side only. This is the charge enclosed. What is the charge enclosed in this side? Sigma, in this case, sigma into s. So what is the charge enclosed if this is the Gaussian surface? Gaussian surface, right? It is the Gaussian surface. Then what is the charge enclosed? Is equal to this side, sigma into s, this side plus sigma into s. It is equal to 2 sigma s, right? And now the electric field will be the uniform. This is the electric field, this is the electric field. How many surfaces of this horizontal cylinder is this? 3. 1, 2, 3. So if this is the s vector, this is the E vector, what is the flux link with this surface? Say E into s, right? What is the flux link with this surface? Say flux is nothing but E into s. What is the flux link with this surface? The electric field is this, and the surface area vector is this. Whether you choose this the ds or s, the angle is what? Say 90 degree. Is it clear? So what is the flux link with this third surface? Say 0. So now apply the Gauss's law. Gauss's law. What is that? The net outward flux is equal to charge enclosed divided by epsilon naught. I think you know this is the charge enclosed upon epsilon naught. The outward flux, although you can write in this way, E dot ds, right, is equal to 2 sigma s upon epsilon naught. So this sigma E dot ds is nothing but like this. You may write this is for this is the closed, this is the integration for the closed surface. This integration for the closed surface may be written or may be divided into the 3 parts. For this one surface, for this one surface, for the surface 3. If this is the surface 1, surface 2, surface 3, in some book it may be written as E dot ds for the surface S1, E dot ds for the surface 2, E dot ds for surface 3 is equal to 2 sigma s upon epsilon naught. You understand or not? Right. So this is the, this is phi 2 is nothing but E dot ds for the surface 2, which is equal to what? It will comes to be the E into s. You understand or not? Fine. If you consider this is the surface S1, so what is this? Integration of E dot ds for the surface 1, it is also equal to, and what is this? The angle is 90 degree, so its value is 0, right? It may be written in phi 1, phi 2, phi 3. So I am writing this side, this value is what? Es, this value is what? Es, this value is what? 0, right? 2 sigma s upon epsilon naught, or it may be written as phi 1 plus phi 2 plus phi 3 is equal to total charge enclosed divided by epsilon naught. In this way also you can write. So this is the 2 into s is equal to 2 sigma s upon epsilon naught. The s cancel out. So electric field is what? Sigma upon epsilon naught. Whether the electric field due to the non-conducting sheet is 2 sigma upon epsilon naught, sigma upon 2 epsilon naught. Here the electric field due to conducting sheet, due to conducting sheet. So you have to remember conducting sheet sigma upon 2 epsilon naught, it is sigma upon 2 epsilon naught. Why it is so? Because in conducting sheet the two sides the charge distribution are to be considered. If in the non-conducting sheet one side is sigma, other side is also given as the sigma, then the electric field again will be sigma upon 2 epsilon naught, similar to the conducting sheet. But generally they give that, they say in the question that the sheet of the surface charge density is the sigma, then the electric field you must have to take sigma 2 upon epsilon naught until unless they mention the sheet is conducting. If the sheet is conducting and the surface charge density is given as the sigma, so you have to write the electric field sigma upon epsilon naught, right? Copy this. So read this question. In this question, the electric field component as shown in figure. What is the figure? This is the x-axis and this is the y-axis, this is the z-axis, and this is the cube, right? This is the cubical surface, right? Like this. This is the cubical surface. All right. So this is distance A. This distance is also equal to the A. All right. This is A. This is also equal to the A. So one surface is this, the another surface is this, because the area is what? Say A, and the electric field is given only in the x direction. Is it alpha root x, and the y direction and z direction electric field is what? 0. So electric field only present in the x direction, that is like this, like this, like this, like this, right? Here the electric field is along the positive direction, so this is the flux phi 1, which is the outward flux. In this case, the flux is what? Say entering. In this case, on this surface the flux is entering, and for this surface the flux is coming out. So on this surface the flux is what? Say phi 2. This is the inward flux, which will be negative, and this is the outward flux, right, will be the positive. So to find the flux is nothing but it will be positive E into area. In this case, the phi 2 will be negative E into area. Here the E, you may write it is the phi 2, it is the phi 1, right? Phi 2 and phi 1, right? The electric field at this point is what? Assumed to be the E2, and the electric field E2. How to find the electric field E2? I will put the value of the x at this distance. The x is equal to what? Say 2a. So here the x is equal to 2a. For this plane, the x component, x distance is 2a. So alpha, this is x is equal to 2a. So the E2 will be equal to what? Alpha into 2a. While the electric field at this point, the electric field, at this point this is the electric field. So at this point the electric field E1 will be alpha into root a, because the x value is over here is equal to a, right? So this is the inward flux, alpha root a into s, and this is the outward flux, E2 into s. The E2 is alpha root 2a into s. What is the s? S is the area. The area is nothing but the a square. Area is nothing but a square. So this is the phi 2 and this is the phi 1. So the first question, the flux through the cube. Listen one thing, there will be the 4 faces again. This the face, this is the face. All the flux link with the other faces other than first and the second, the 0. So the total flux is nothing but the inward flux plus outward flux. It is minus alpha root a into a cube, a square, plus alpha root 2a into a square. So alpha a square, if you take common, minus root a plus root 2a. Are you getting? If you take the root a common, right, minus 1 plus root a you will get. So this is the total flux is equal to alpha a square into a ki power 1 by 2 is equal to a ki power 5 by 2, a ki power 5 by 2, and this is root 2 minus 1 is the total flux link in this surface, link with this cube. Is it clear or not, you tell? Oh, okay. The value is also given. The value of alpha is what? The value of alpha is 5 Newton per Coulomb, right? Meter 1 by 2. It is the SI unit only. The alpha value is 5. You can say right like this, right? And what is the value of A? Is equal to 1 meter. So total flux is 5, 1 ki power 5 by 2, root 2 minus 1. It is equal to 5, 1.41 minus 1. Fine. This is 5 into 0.41. 5 chok 20, right? This is the total flux is equal to Newton per Coulomb meter square. Right? Copy this. So what is the second part? In the second part, you have to find the charge enclosed in this cube. So the charge enclosed, you have to find the charge enclosed it can be found with the help of the Gauss's law. What is the Gauss's law? The net outward flux is equal to charge enclosed divided by epsilon naught. So what is the net outward flux? This is net outward flux. Net outward flux. So you tell, this is the inward, this is the outward. So what is this? Is the total flux. This is only the net outward flux. So it is 2.05 charge enclosed divided by epsilon naught. So the charge enclosed is nothing but 2.05 into epsilon naught. The value of the epsilon naught is 8.85. 8.85 into 10 to the power minus 12. When you will simplify this, you will get approximately 1.77 into 10 to the power minus 11 coulomb, right? So there will be different type of the question, similar type of the question. They will ask what is the charge enclosed in this cube, right? So the charge enclosed, to find the charge enclosed in this cube, you have to find first the total outward flux linked with this surface, linked with this closed surface, and then apply the Gauss's law, and you will get the charge enclosed in this cube. Is it clear? So this is the charge enclosed. Copy this. So read this question. In this question, the two positively uniformly positively charged infinitely long wires. This is the one wire, the infinite, the linear charge density is lambda 1. There is another wire, the linear charge density is lambda 2. Getting or not? And on the x-axis, this is the y-axis, right? X is equal to minus a, x is equal to plus a, right? The x coordinate where the electric field is 0. Listen one thing. Although the lambda 1 is greater than the lambda 2, right? So if both were lambda, so this will be the point where the electric field is 0. And due to line charge, did you remember? You have to remember the formula. At distance r, 2k lambda upon r is the electric field. But if this is the lambda 1 which is greater than this lambda 2, so the point will not be, null point will not be in the mid, rather it will be shifted to this point, right? Because its magnitude will be, if this is the 1, the E1 will be in this way, and if this is the E2, because of this, the E2 electric field will be in this direction. So if you assume this distance is to be x, and therefore this is the A, so the E1, because of this line charge, the E1, if you want to write, the electric field is nothing but 2k lambda 1 upon A plus x, and towards the right. What is the E2? Is the electric field due to this, at this point the electric field towards the left, it will be 2k lambda 2 upon A minus x, because this distance is A and this is x, so this distance it will be what? Say A minus x, right? Here the electric field at this point is 0, right? If electric field at point P is 0, then E1 and E2 must be equal and opposite direction. So therefore 2k lambda 1 upon A plus x1, right, is equal to 2k lambda 2 upon A minus x. 2k is cancelled out, you simplify this, and the value of the x we can get, right? It is lambda 1a, lambda 1x, lambda 2a, lambda 2x. Fine. If it goes, if you simplify this, lambda 2 into x, this is x. So if you take the x common, lambda 1 plus lambda 2 is equal to lambda 1 minus lambda 2 into a. So the x is equal to what? Lambda 1 minus lambda 2 plus lambda 2 into a, right? So this is the value of the x. This is the distance from the origin of this point P where the net electric field is 0. All right, copy this.